We are dealing with lecture 2 of atom. So in this we are going to discuss about the developments of Bohr model of an atom. Bohr model of an atom. So what are the developments that took place under the guidance of Niels Bohr? So it all happened in between 1913 and 1915 when this was established for one electron system. So the first thing which I write is the applicability. So I am writing the Bohr model is appropriate. The Bohr model is appropriate for one electron system. For one electron system. So now when I say one electron system, so I mean to say that it is applicable for, so like hydrogen atom, He plus ion, Li plus 2 ion, etc. So all these are examples of one electron system. So it was not giving a true picture of even these simple atoms, and the entire theory was finally given by the quantum mechanical uh, model, which is different from the Bohr model in several fundamental ways. But for the time being, we will be studying about the Bohr model and the postulates that governs the Bohr model. So we are first of all establishing the postulates for the Bohr model. So we are coming to the first postulate. So now if I state the first postulate, so the statement states that during revolution of electron around the nucleus in the circular orbit, the electric Coulomb's force on electron is balanced by the centrifugal force acting on it in the rotating frame of reference. So what I exactly mean to say by this particular statement is that if we are considering a atom with atomic number Z, so the charge inside the nucleus is plus Ze, and the electron is orbiting around it in a circular path like this, and I am considering that this electron over here will experience electrostatic force of interaction between the nucleus and the electron, which we are symbolizing as Fe, that is electrostatic force, which is balanced by the centrifugal force, which is acting in the outward direction. So this is what I mean to say, that when I state during revolution of electron around the nucleus, that is when it is traveling with a velocity v around the nucleus in a circular path of radius r, the electrical force or the electrostatic force on the electron is balanced by the centrifugal force acting on it in the rotating frame of reference. So over here, if I write the force equation, so I can state from here that the force mv square upon r is equal to the electrostatic force, which is written as k q1 q2 by r square. So when I say k q1 q2 by r square, so we mean to say something like this. And over here, if I rewrite this statement, so then I can write it in this way, that mv square is equal to ze square upon 4 pi epsilon naught r. So this is a deduction from the first postulate of Bohr model, that is mv square is equal to 1 upon 4 pi epsilon naught ze square upon r. So now we are coming to the second postulate. So we are discussing about the second postulate of Bohr model. The second postulate states that during the revolution around the nucleus, the orbital angular momentum of electron is an integral multiple of Planck constant divided by 2 pi. So basically, I mean to say that if we are considering this nucleus having atomic number Z, that is the total positive charge inside the nucleus as Ze, and the electron is moving in a circular path around the nucleus with a speed v in a radius r. So we state over here that the angular momentum for electron, which will be written as mvr. So we are not considering the rotational aspect of the electron. We are considering electron as a point particle which is moving in a circle of radius r. So we are writing it as mvr, and this is equal to the integral multiple of, that is n times of h upon 2 pi, where h is regarded as the Planck constant. So this statement is coming from the second law. Now this h upon 2 pi is several times written as h bar. So we can say that h upon 2 pi is several times written as h bar. You may find this in some textbook. So kindly get confused. So they cut the h bar and they write it as h upon 2 pi. So now from these two postulates, we can evaluate the value of speed and radius of the nth Bohr orbit. So now what we are exactly doing from here is that I am stating that V can be written as nh upon 2 pi mr, and we will be substituting this value of speed in the first equation. So this is the deduction from the second postulate which I am mentioning as 2, and we will put this value in the previous obtained condition, that is mv square is equal to ze square upon 4 pi epsilon naught r. So if I put this in this aspect, that is mv square is equal to ze square, so we can write from equation number 1 that we have attained mv square is equal to ze square upon 4 pi epsilon naught r. So if I substitute the value of v from the second equation, so we will obtain it as, so we can write this equation as m v square will be written as n square h square upon 4 pi square m square r square is equal to ze square upon 4 pi epsilon naught r. So from here, if we perform a basic calculation, that is if we chop out 4 pi, this m from here and this r from here, so we obtain a equation for r. So r is attained as, that r can be written as n square h square epsilon naught upon pi m z square. So this is the equation for the radius of the nth Bohr orbit that we attain, that r is equal to n square h square epsilon naught upon pi m z square. So if we look at this expression, that is if I rewrite this expression over here, that r equals n square h square epsilon naught upon pi m z square, so the result that we obtain from here, so we can say that this value is having all these as constants. So over here, the entire parameter of h square epsilon naught pi m e square is constant. So the only parameter that is going to vary for an atom and atom to atom is the value of the quantum number, principal quantum number n, and the value of atomic number z. So if I evaluate the value for all these constant, so we attain that r is turning out to be 0.53 n square by z, and the value will be in angstrom. So this is the value that we are going to attain from this particular expression. and this equation must be remembered so that we can calculate the value of radius of nth Bohr orbit whenever the value of the principal quantum number and atomic number is mentioned. So the next one that we come across is the velocity of electron in nth Bohr orbit. So now we are coming to the calculation of velocity of electron in nth Bohr orbit. So if we come to the calculation of velocity of electron in the nth Bohr orbit, so from here we have written from the second postulate that V is equal to nh upon 2 pi mr. So this is the expression that we have written from the second postulate nh upon 2 pi mr. So if I substitute the value of r, the value of r which we have attained, that is if I write it as nh upon 2 pi m, and then if I write the value of r which is equal to n square h square epsilon naught upon pi m z square. So we have put the value of r from this particular expression, and over here we can say that nh will be cancelled from here, pi m will be cancelled from here, and the expression is left in terms of ze square upon 2 nh square epsilon naught. So over here we can again see that this expression, that is we obtained as ze square upon n into 2h epsilon naught. So if we again consider this formula for velocity, so we see that the entire parameters of e square upon 2h epsilon naught is constant and is not going to fluctuate for a particular atom, and hence I can say that the velocity for the nth Bohr orbit is proportional to z by n. And similarly, if I substitute the value for the constants, we attain the velocity in the nth Bohr orbit is turning out to be 2.18 into 10 to the power 6 z by n. The value is in meter per second. So this is the result that we obtain for the velocity or the speed of an electron in the nth Bohr orbit. So these are the two deductions which we have come across over here for a particular Bohr orbit. That is, we have calculated the values of r and v respectively. So using the expressions for the radius and velocity, we are evaluating many other expressions for the same. So the first thing that we are going to calculate is the value of angular velocity for electron in nth Bohr orbit. Angular velocity of electron in nth Bohr orbit. So if we come for this particular calculation, then we can say that omega for the nth Bohr orbit can be written as v upon r. That is speed at the nth Bohr orbit divided by the radius. So if I substitute the value for v and n, so for v and r respectively, so we attain from here that v is can be written as ze square upon twice of nh epsilon naught, and r can be written as n square h square epsilon naught upon pi m z square. So if we consider this particular equation, so from here we can evaluate the value for the omega. So from here I can say that we are attaining the value as equal to, so the omega n is turning out to be, so from above we get pi m z square e to the power 4 upon twice of n cube h cube epsilon naught square. So we are getting an expression like this for the angular velocity of the electron in the nth Bohr orbit. So what is important for you to understand over here is that you will not be able to remember all these absurd equations. So it is important that you quickly write the first and second postulate of Bohr and then evaluate the value of velocity and the radius, and then the rest of the calculation can be done very quickly. The next thing which I calculate over here is the frequency for the electron in nth Bohr orbit. So if I calculate over here the frequency of an electron in the nth Bohr orbit, so over here we can write the frequency for electron in the nth Bohr orbit is equal to omega n upon 2 pi. So if I just divide this value by 2 pi, then we can attain this value. And over here, we are attaining that the frequency for the nth Bohr orbit is turning out to be pi m z square e to the power 4 upon twice of n cube h cube epsilon naught square times of 1 by 2 pi. So pi and pi will cancel out and we get frequency for the nth Bohr orbit is turning out to be m z square e to the power 4 upon 4 times of n cube h cube epsilon naught square. So we obtain an expression like this for this particular problem, that is, this is the frequency for the nth Bohr orbit. The frequency of an electron in the nth Bohr orbit can be calculated in this sense. And the next thing which we calculate over here is the time period of electron in nth Bohr orbit. So if I write time period of an electron in the nth Bohr orbit, so over here I can write that the time period is written as inverse of frequency. So if we just reverse the equation that we have attained previously, so we can quickly get the value for the time period. That is, I can write it as 4 n cube h cube epsilon naught square 4 n cube h cube epsilon naught square upon mz square e to the power 4 mz square e to the power 4. So this becomes the equation of time period for the nth Bohr orbit. So this is the expression for the time period for the nth Bohr orbit. Now we come to the most important aspect, that is using the equation for the radius and speed or the velocity v, we are trying to calculate the energy profile. And after we calculate the energies, we will be giving the third postulate for the Bohr model. So I am calculating the energies associated, energy profile for the electron system. So if we discuss the energy profile for the electron system, so in the atom of an element, that is, there is a nucleus which is having the positive charge plus Ze, and the electron is revolving in it with a speed v in a orbit radius r. So over here, the potential energy due to the interaction between the nuclear charge and the electron is because of the attractive force, and hence the potential energy will be written with a negative sign. So I am saying that potential energy is due to the electrostatic interaction between the nuclear charge and the electron, and since the force is attractive in nature, the potential energy will be negative. So we write potential energy as minus k q1 q2 upon r. So if we calculate the value for potential energy, then we can write it as U is equal to minus ZE square upon 4 pi epsilon naught. And if I put the value for R over here, then we will put it as N square H square epsilon naught upon pi m ZE square. So this is the expression for the potential energy that we are evaluating, and on simplifying we can write it as U is equal to minus of Z square pi m e to the power 4 upon n square 4 pi epsilon naught square h square. So over here we are attaining an expression like this. We can again cancel out pi, and we can write the equation for potential energy as minus of m e to the power 4 upon 4 epsilon naught square h square z square by n square. So I can say that potential energy will be depending upon the z square and n square parameter. So this is the expression for the potential energy that we have evaluated, and we can say that it is depending upon z square and n square parameter. The next thing which I am going to do over here is that we will be calculating the value of kinetic energy associated with this electron in the nth Bohr orbit. So we are trying to evaluate kinetic energy. So if I write the equation for the kinetic energy, then the kinetic energy is going to be positive, and it will be simply written as half mv square. So if we write the expression for kinetic energy, then it is equal to half m, and if I put the value of v, then it is equal to z e square upon twice of n h epsilon naught. So we are putting the value of a velocity that we have evaluated earlier, and we are squaring this term. So we attain half m z square e to the power 4 upon 4 times of n square h square epsilon naught square, and hence the kinetic energy is turning out to be mz square e to the power 4 upon 8 h square epsilon naught square n square. So again we are seeing that this also depends upon m e to the power 4 upon 8 h square epsilon naught square z square by n square. So it is a positive quantity, and I can say that this expression is again proportional to z square by n square. So if we look carefully from the equation of the potential energy, which is minus of m e to the power 4 upon 4 h square epsilon naught square z square by n square, and the expression for kinetic energy, which is stating m e to the power 4 upon 8 h square epsilon naught square z square by n square, we are in a position where we can write the total energy for the electron in nth Bohr orbit. So if I calculate the total energy for the electron in nth Bohr orbit, total energy of an electron in nth Bohr orbit, then I can say that the total energy associated with the electron in nth Bohr orbit is the sum of potential energy and kinetic energies. So if I can simply add the two values, that is of potential energy and kinetic energy, which we have attained previously, so we will attain, or we can write, the total energy of an electron in the nth Bohr orbit. So if I come to this expression for potential energy, which we have obtained as minus m e to the power 4 upon 4 epsilon naught square h square z square by n square, and if we come to this expression where we have attained the kinetic energy value as m e to the power 4 upon 8 times of epsilon naught square h square z square by n square. So if I substitute these two values over here, so I can write it as that the total energy is equal to minus m e to the power 4 upon 4 times of epsilon naught square h square z square by n square plus the kinetic energy value, which is equal to m e to the power 4 upon 8 times of epsilon naught square h square z square by n square. So from here we can say that the total energy is turning out to be. So I can say over here that we can write from these two expressions of potential energy and kinetic energy that total energy is equal to minus kinetic energy is equal to potential energy by 2. I don't know if you can see this coming up, but over here we have attained a similar expression that the total energy is turning out to be minus of m e to the power 4 upon 8 epsilon naught square h square z square by n square. Because over here, if in the potential energy equation, if I just multiply by half, then the value will be of the magnitude will be of the kinetic energy value. So we attain this expression, and this is a very important result which will be helping us in analyzing several problems. That total energy is equal to minus kinetic energy is equal to potential energy by 2. So over here, if I look at the expression for the total energy, then I can say that these parameters are constant. These parameters are constant, and if we evaluate these parameters, then we attain the total energy value is turning out to be minus 13.6 z square by n square in electron volt. So this is going to be the total energy equation for the electron in the nth Bohr orbit. So it is coming out to be minus 13.6 z square by n square in electron volt. Now it is very important over here for you to understand that all these equations which we have obtained, so among them I am marking a few equations which must be kept in mind. So this is one of those equations which must be kept in mind. This is one of those expressions which must be kept in mind. If we come previously, then this is the expression of the velocity and radius which must be kept in mind, because if you remember these parameters, then you will be able to calculate the rest of the parameters very easily. And the velocity and radius can be very quickly calculated if you just write the expression that by balancing the centrifugal force and the electrostatic force, and the next one can be written with the second postulate, that is the angular momentum is quantized. After the calculation of the total energy, I am stating the third postulate of Bohr. So I am stating the third postulate. So I am stating the third postulate of Bohr. So third postulate stated that while revolution of an electron is in an orbit, its total energy is taken as the sum of its kinetic and potential energy values due to the interaction with the nucleus. And what exactly happens is, while revolving around the nucleus in an orbit, it is in a stable state, that is, it does not emit any energy radiation during revolution. I am stating one more thing. This is in contrast with the Rutherford explanation. That is, while revolving around the nucleus in an orbit, it is in a stable state. It does not emit any energy radiation during revolution. It emits energy radiation only when it makes a transition from the higher energy level to a lower energy level, and the energy of the emitted radiation is equal to the difference in energies of the electrons in the two corresponding orbits in transition. So basically, I am stating that while revolving while revolving, electrons do not emit any energy radiation. Any energy radiation. The energy is emitted. The energy is emitted only during the transition of electron. The transition of electron from higher energy level to lower energy level. From higher energy level to lower energy level, and the energy emitted is equal to the difference in energy of two energy levels. So this is the third postulate of Bohr, which is we are going to continue in the next lecture when we will be drawing energy level diagrams for a hydrogen atom.